February 12th, 1944. Rabaul, New Britain. Senior Petty Officer Takeo Yamamoto crouched behind his Type 96 25mm anti-aircraft gun, tracking what appeared to be easy targets. 4 American fighters had just completed their strafing run on the airfield below and were climbing away at a leisurely pace. Yamamoto had served in this position for 8 months. He had shot down 3 American aircraft. He understood bullet drop, deflection angles, and the predictable flight paths of climbing fighters. He led the nearest aircraft by 3 aircraft lengths, exactly as training prescribed. His finger tightened on the trigger. Then the American fighter did something that violated every principle of aerial combat Yamamoto understood. Instead of continuing its climb to safety, the fighter rolled inverted and dove directly toward his gun position. Not a gentle dive. A vertical plunge that accelerated impossibly, the Pratt Whitney engines screaming at full power, 400 miles per hour, 420, 450 miles per hour, in a near-vertical dive that should have torn the wings from any aircraft ever built. Yamamoto watched through his gun sight as the fighter dove past the altitude where it should have begun its pullout. Past the altitude where structural failure should have occurred. The American was going to impact the ground at terminal velocity, except he didn't. At less than 500 feet altitude, the Corsair pulled out of the dive with a violence that should have killed the pilot through G-forces alone. The wings bent visibly upward, flexing like a bird's wings, then snapped back to their original shape. The aircraft leveled off, its 650 caliber machine guns hammering Yamamoto's position, and climbed away at full power before he could even track it with his gun. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. 3 more Corsairs repeated the same maneuver in sequence. Vertical dives exceeding 450 miles per hour. Impossible pullouts that defied physics. Yamamoto's entire gun crew survived, but they understood something fundamental had changed. American aircraft were no longer bound by the structural limits that governed Japanese fighters. The chance-vought F4U Corsair could do things that should have destroyed it, and Japanese gunners could no longer predict where it would be. The shock had been building for months across every Japanese-held island, from the Solomons to the Marshalls. Since the Corsair's combat debut in February 1943 with Marine Squadron VMF 124 at Guadalcanal, Japanese forces had encountered an aircraft that rewrote the fundamental rules of dive bombing and ground attack. The terror wasn't the speed alone. Japanese pilots had encountered fast American aircraft before. The terror was the combination of that speed with the ability to pull out of dives that should have been fatal, deliver devastating accurate fire, and climb away before defensive fire could respond. Understanding Japanese shock at the Corsair requires understanding what came before it. Japanese naval aviation in 1942 had been optimized around the Zero fighter, an aircraft that emphasized maneuverability and range over everything else. Wing loading on the Zero measured 24.3 pounds per square foot. The aircraft could turn inside anything the Allies could field, but it achieved this performance through radical weight reduction. The aluminum skin measured 0.032 inches thick. There was no armor protecting the pilot. There were no self-sealing fuel tanks. The Zero's designers had made a conscious choice. Sacrifice protection for performance. Sacrifice structural strength for maneuverability. The result was an aircraft that dominated early Pacific combat but couldn't survive. Punishment. American designers had made the opposite choice with the Corsair. The chance-vought F4U incorporated the most powerful engine available in 1942. The Pratt Whitney R2800 Double Wasp produced 2,000 horsepower in early models, reaching 2,250 horsepower with water injection in later variants. This engine alone weighed 2,360 pounds, more than the empty weight of many pre-war fighters. Rather than compromise, chance-vought engineer Rex Beisel built the entire aircraft around the engine's capabilities. The result was a fighter bomber that weighed 12,000 pounds empty and over £14,000 fully loaded for combat missions. For comparison, the Zero weighed £3,900 empty. The Corsair was more than 3 times heavier than its primary opponent. Japanese intelligence officers who examined reconnaissance photos of Corsairs at Henderson Field in February 1943 filed reports that circulated through Imperial Navy headquarters. The American machine appears abnormally large for a carrier fighter, one report stated. The inverted gull wing configuration suggests unusual design priorities. Intelligence indicates it may weigh over 6 tons fully loaded. Either our intelligence is mistaken, or the Americans have achieved structural strength we cannot match. The intelligence was not mistaken. The Corsair's distinctive inverted gull wing wasn't an aesthetic choice. It was a structural solution to conflicting requirements. The massive 13-foot, 4-inch diameter propeller needed ground clearance for carrier operations. The landing gear needed to be as short as possible to reduce weight and complexity. The inverted gull wing allowed the landing gear to attach at the wing's lowest point, keeping strut length minimal while giving the propeller adequate clearance. But that design choice had profound structural implications. The wing root, where the wing joined the fuselage, experienced enormous bending forces during high-G maneuvers. The inverted gull design placed the wing root at nearly 90 degrees to the fuselage, creating a natural structural brace. But it also meant the wing had to be extraordinarily strong to handle the stress. Chance Vought engineers designed the wing with multiple spars running the entire wingspan. The main spar was a massive aluminum I-beam that could support the entire aircraft weight multiple times over. The skin was thick, flush-riveted aluminum that added structural strength rather than simply serving as a covering. The result was a wing that could handle stress loads that would have torn a Zero apart. In testing at the Naval Air Test Center in Patuxent River, Maryland, engineers subjected Corsair wings to 12 G-forces, 12 times the force of gravity. The wings flexed upward dramatically, bending visibly, but they didn't fail. They returned to their original shape when the load was removed. No Japanese fighter could withstand forces above 7 Gs without risking catastrophic structural failure. The Corsair's margin of safety was almost double that of its opponents. This structural strength translated directly into tactical capability that Japanese forces found impossible to counter. The first combat missions revealed the pattern that would repeat across the Pacific for the next 2 years. Marine Captain Ken Walsh, flying with VMF-124 from Guadalcanal, engaged Japanese aircraft on February 15, 1943, during the Corsair's first combat sweep. His after-action report described a Zero attempting to escape by diving away from his attack. Walsh followed in his Corsair, diving from 20,000 feet to 8,000 feet at speeds exceeding 420 miles per hour. The Zero pilot attempted to pull out at 8,000 feet. Walsh watched the Japanese fighter's wings fold upward and tear completely off the fuselage. The Zero disintegrated in mid-air, scattering pieces across the sky. Walsh pulled out of his dive at 6,000 feet, experiencing forces his aircraft shrugged off effortlessly. The structural margin that saved Walsh would save thousands of American pilots over the next 2 years. Japanese pilots learned quickly that diving away from a Corsair meant certain death. The American fighter could follow any dive, exceed any speed, and pull out lower than any Japanese aircraft could match. Japanese anti-aircraft gunners faced an even more impossible problem. Traditional dive bombing required aircraft to begin their dive from altitude, build speed gradually, release ordnance at a predictable altitude, and pull out with enough margin to avoid ground impact. Gunners learned to predict the pull-out point and concentrate fire there. The bomber was most vulnerable during pull-out when it was flying straight and level, slowed by G-forces, and couldn't maneuver aggressively. The Corsair changed these equations completely. Marine and Navy pilots discovered they could begin dives from any altitude, accelerate to speeds exceeding 450 miles per hour, maintain that speed throughout the dive, deliver ordnance or gunfire with devastating accuracy, and pull out at altitudes below 500 feet. Japanese gunners had perhaps 2 seconds to acquire, track, and fire on a target moving at 450 miles per hour. By the time they reacted, the Corsair was already pulling away in a climb, using its massive engine power to regain altitude before the next attack. Lieutenant Colonel Harold Bauer, commanding officer of VMF 212, developed the tactic that became standard doctrine across Marine Corsair squadrons in the Solomons. His pilots called it the Corsair Slash. Approach the target at 20,000 feet altitude, maintaining formation. Identify anti-aircraft positions and concentrations. Roll inverted and enter a vertical or near-vertical dive directly toward the target. Accelerate to maximum speed, typically 450 to 480 miles per hour indicated. Fire all 6 50 caliber machine guns in a concentrated burst from 1,500 feet to 500 feet altitude. Pull out hard at 500 feet, accepting 8 to 9 G-forces. Climb away at full power using speed gained in the dive. Japanese gunners found this tactic essentially impossible to counter. Senior Petty Officer Takeo Yamamoto, the same gunner who witnessed the February 12th attack, wrote in his diary about the psychological impact. "We cannot track them," he recorded on February 20th. "They appear from above, moving faster than we can traverse the gun. By the time we begin firing, they have already attacked and are climbing away. We hit nothing but air. The fear is not of being hit. The fear is of being helpless, unable to respond, unable to defend." The material evidence of Corsair attacks multiplied across Japanese-held positions throughout 1943. At Munda Airfield on New Georgia, a single Corsair attack on April 8 destroyed 9 parked aircraft and damaged the runway in a single pass lasting less than 30 seconds. The pilot, First Lieutenant Robert Hansen, dove from 18,000 feet to 400 feet, fired 800 rounds from his 6 machine guns, and climbed away without receiving a single hit from ground fire. Japanese after-action reports noted that defensive fire had been heavy and accurate, with multiple guns tracking the target throughout its attack run. But at 450 miles per hour, accurate fire meant nothing if the target had already moved before bullets reached its position. The Corsair's dive capability enabled close air support missions that would have been suicidal in any other aircraft. Marine pilots supporting ground forces on Bougainville in November 1943 routinely made strafing runs at Kuparuk site, targets less than 200 yards from friendly positions. The tactic required diving from altitude at speeds exceeding 400 miles per hour, firing a precise burst, and pulling out immediately to avoid overshooting into friendly lines. The structural strength allowed pullouts with minimal altitude loss. Pilots could deliver fire danger close to friendly troops and pull away safely. Japanese ground commanders filed increasingly desperate reports about the impossibility of defending against these attacks. Major General Masao Maruyama, commanding Japanese forces on Guadalcanal, wrote in October 1943 that American air attacks had made daytime movement impossible. "The enemy aircraft dive at speeds we cannot counter," he stated. "They attack individual soldiers, vehicles, supply dumps. They appear without warning, strike with precision, and vanish before we can respond. Morale collapses when men realize they are completely defenseless. The firepower itself compounded the terror." The F4U carried 6 Browning M2 50 caliber machine guns, 3 in each wing, mounted outboard of the propeller arc. Each gun fired at 850 rounds per minute. A 1-second burst sent 85 rounds downrange, each projectile weighing 0.7 ounces and striking with over 12,000 foot-pounds of energy. In a typical strafing run lasting 3 seconds, a Corsair delivered over 250 rounds of 50 caliber ammunition. Japanese soldiers learned that structures offering protection against rifle fire provided no protection whatsoever against 50 caliber machine guns. Wooden buildings disintegrated. Sandbag positions were torn apart. Light vehicles were shredded. Personnel caught in the open were killed instantly by projectiles that could tear a human body apart. Corporal Hiroshi Tanaka, an infantry soldier who survived the Bougainville campaign, described a Corsair attack in his memoir, published in 1968. The sound arrived first, he wrote, a rising scream of the engine in a dive. Then the impacts, explosions of dirt and debris walking toward our position. I pressed myself into the earth and prayed. The attack lasted perhaps 5 seconds. When I looked up, 3 men in my squad were dead. The truck behind us was in pieces. The Corsair was already 1,000 meters away, climbing. The psychological dimension extended beyond the immediate terror of attacks. Japanese forces understood that the Corsair represented American industrial and engineering capability they couldn't match. The aircraft's massive size, its powerful engine, its structural strength, all demonstrated material superiority that no amount of courage or skill could overcome. Japanese fighters were limited by what their industry could produce. Aluminum alloys were inferior. Engine development lagged behind American progress. Manufacturing capacity couldn't match American output. Lieutenant Commander Tadashi Nakajima, an experienced Japanese fighter pilot with 41 victories who survived the war, wrote in his 1952 memoir about encountering Corsairs over Rabaul in March 1944. I engaged what I thought was an easy target, he stated. A single American fighter separated from its formation. I attacked from above and behind, the perfect position. I fired a long burst from both cannon and machine guns. I observed strikes on the fuselage and wing. Any Zero would have exploded or caught fire immediately. The American aircraft shuddered slightly and continued flying. The pilot rolled hard right and dove away at a speed I couldn't match. I pursued for perhaps 30 seconds before abandoning the chase. He was still accelerating when I lost visual contact. The durability of the Corsair added another dimension to Japanese frustration. The R2800 engine could sustain tremendous damage and continue running. The radial configuration meant that even if several cylinders were destroyed, the remaining cylinders could maintain power. The aircraft's size meant critical systems had spacing and redundancy. Self-sealing fuel tanks prevented fires. Armor plating behind the pilot's seat stopped most small arms fire. The massive radial engine served as additional armor, protecting the pilot from frontal attacks. Maintenance records examined after the war revealed Corsairs that had returned to base with astonishing damage. One F4U flown by First Lieutenant Robert Hansen returned to base on Bougainville in August 1943 with 37 holes from 20mm cannon fire, 14 holes from 7.7mm machine gun fire, and extensive damage to the vertical stabilizer. The aircraft was repaired and returned to combat status within 48 hours. Another Corsair flown by Captain Kenneth Walsh took a 20mm cannon round directly through the oil cooler, losing oil pressure and smoking heavily. Walsh flew 75 miles back to base at reduced power and landed safely. The engine was replaced, and the aircraft returned to service within 24 hours. This resilience broke Japanese pilot morale in ways that statistics alone couldn't capture. Scoring hits meant nothing if the target didn't go down. Pilots expended precious ammunition, took enormous risks maneuvering into firing position, scored solid hits with cannon fire, and watched their target fly away trailing smoke but still flying. Meanwhile, if a Corsair's 650 caliber machine guns hit a Zero or Oscar or Tony, that Japanese fighter was finished. The thin aluminum skin provided no resistance. The unprotected fuel tanks ignited immediately. The unarmored pilot was killed or wounded by the first burst. The ground attack capability evolved throughout 1944 as Marine and Navy squadrons experimented with ordnance loads. The F4U could carry 2,000 pounds of bombs or 8 5-inch high-velocity aircraft rockets in addition to its 6 machine guns. Marine pilots discovered that the structural strength allowing 450-mile-per-hour dives also allowed accurate dive bombing with heavy ordnance. Traditional dive bombers like the SBD Dauntless released bombs at relatively shallow angles to avoid excessive G-forces during pullout. The Corsair could dive nearly vertically, release ordnance at low altitude for maximum accuracy, and pull out safely. If you find this story engaging, Please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. First Lieutenant Robert Hansen, who would become the Marine Corps' leading Corsair ace with 25 confirmed victories before his death in February 1944, pioneered dive-bombing tactics that became squadron doctrine. His technique involved approaching the target at 15,000 feet, identifying the exact aim point, rolling inverted and entering a 70-degree dive, accelerating to 430 miles per hour, releasing bombs at 1,500 feet altitude and pulling out at 500 feet. The technique delivered bombs with accuracy, approaching that of dedicated dive bombers, while exposing the aircraft to defensive fire for only seconds. Japanese defenders at Rabaul experienced these tactics throughout late 1943 and early 1944 as Marine Corsair squadrons systematically destroyed the base's infrastructure. Colonel Masatake Okumiya, a senior Japanese naval aviation officer stationed at Rabaul, described the psychological impact in his post-war memoir. "We could do nothing," he wrote. "The Americans attacked from altitudes and speeds that made interception impossible. Our fighters couldn't reach them before they dove. Our anti-aircraft fire couldn't track them during their dives. They destroyed fuel dumps, supply warehouses, parked aircraft, repair facilities, everything we needed to continue operations. The base became untenable, not through a single decisive battle, but through systematic destruction of our capability to function." The statistics from 1944 demonstrate the Corsairs' impact on Japanese forces. Marine Corsair squadrons in the Solomon Islands campaign flew approximately 22,000 combat sorties between February 1943 and November 1944. They claimed 2,106 confirmed aerial victories against Japanese aircraft. They destroyed an estimated 12,000 ground targets, including vehicles, buildings, supply dumps, and parked aircraft. They dropped over 35,000 tons of ordnance. The loss rate was remarkably low, approximately 2% of sorties flown, testament to the aircraft's speed, structural strength, and ability to absorb damage. Japanese aircraft losses in the same theatre exceeded 8,000 aircraft from all causes, including combat, accidents, and operational losses. Corsair attacks accounted for a substantial portion of these losses, both through aerial combat and ground attacks on airfields. The replacement rate for trained Japanese pilots had fallen catastrophically by mid-1944. Average flight training time dropped to 150 hours compared to 400 hours in 1941. American pilot training averaged over 700 hours by 1944. Japanese rookies in obsolescent fighters faced American veterans in superior aircraft. The outcome was predictable and tragic. The tactical innovations developed by Corsair squadrons became templates for close air support doctrine that the Marine Corps uses to this day. The high-speed diving attack, the emphasis on first-pass accuracy, the immediate egress at low altitude using speed, the coordination between ground controllers and attacking aircraft. These principles were refined in combat against Japanese forces who had no effective encounter. Marine Captain Ken Walsh, who survived the war with 21 confirmed victories and received the Medal of Honor, described the evolution of Corsair tactics in a 1963 interview. "We learned quickly that the aircraft's greatest asset was its structural strength," he stated. "We could dive faster and pull out lower than any Japanese aircraft. Once we understood that fundamental advantage, tactics became obvious. Never fight on their terms. Always impose our terms. Use speed and dive performance exclusively." The Japanese had no answer. The human cost of facing Corsairs appeared in Japanese casualty statistics and personal accounts. Corporal Saburo Sakai, Japan's third-ranking ace with 64 confirmed victories who survived the war despite severe wounds, engaged Corsairs multiple times over Rabaul in 1944. His memoir, published in 1957, described the tactical impossibility. "They fight like no aircraft I had encountered," he wrote. "They don't turn. They don't climb slowly. They dive at impossible speeds, fire with devastating accuracy, and climb away before you can respond. If you pursue, they simply accelerate, and you fall behind. If you turn away, they dive on you from above. There is no winning position. You survive through luck or by avoiding combat entirely. Japanese engineering attempts to counter the Corsair through improved aircraft met with limited success, constrained by industrial capacity and resource shortages. The Kawanishi N1 KJ Shiden, introduced in late 1943, was a powerful fighter derived from a floatplane design. It had heavier armament, better armor protection, and performance approaching American fighters. But production problems limited availability. Only approximately 1,400 were built by war's end. Most served in homeland defense rather than forward theaters where Corsairs operated. The Mitsubishi J2M Raiden emphasized speed and climb rate for intercepting high-altitude bombers. It achieved 400 miles per hour maximum speed and climbed at over 4,000 feet per minute. But it suffered from handling problems, mechanical unreliability, and severe production delays. Only 476 were built, far too few to affect the air war's outcome. The Mitsubishi A7M Repu was designed as the true zero replacement with heavy armament, armor protection, self-sealing tanks, and high performance. It never entered combat before surrender. Only 10 prototype and pre-production aircraft were completed. The Zero remained Japan's primary fighter throughout the war because industry couldn't produce replacements in necessary numbers. More than 10,000 Zeros were built despite growing obsolescence. By 1945, Zeros faced not just Corsairs, but also Hellcats, Lightnings, Mustangs, and Thunderbolts. All were faster, more durable, and more heavily armed. The structural strength differential that made the Corsair shocking in 1943 became standard across all American fighters by 1945. Japanese aircraft were simply outclassed in every measurable category. The final irony came in the war's closing months, when Zeros and other Japanese aircraft were adapted for kamikaze operations. The lightweight airframe, originally designed for maneuverability, now carried 550-pound bombs on one-way suicide missions. The philosophy had come full circle. The obsession with offense that led to deleting all defensive equipment culminated in using the aircraft itself as a guided missile. Against these suicide attacks, the Corsair's structural strength proved decisive again. Kamikazes that struck American ships often caused catastrophic damage through fire and explosive force. But Corsairs patrolling combat air patrol intercepted kamikazes before they reached the fleet. The high-speed diving attacks that had terrorized Japanese ground forces proved equally effective against slow-moving kamikazes loaded with bombs and extra fuel. Marine Captain Ken Walsh, by then a squadron commander, described intercepting kamikazes during the Okinawa campaign in April 1945. They flew straight and level at low altitude, making no evasive maneuvers, he stated. We dove from altitude at maximum speed, fired short bursts, and destroyed them before they could reach the ships. The same tactics we had refined against Japanese fighters in the Solomons worked perfectly against kamikazes: speed, altitude, and structural strength. The formula hadn't changed. Post-war analysis revealed that Corsairs accounted for approximately 2,100 confirmed aerial victories against Japanese aircraft from 1943 through 1945. This made it the most successful American fighter aircraft in the Pacific theater measured by aerial victories. The actual number of Japanese aircraft destroyed was certainly higher when including the ground attacks on airfields and unconfirmed combat claims. The Corsair flew 64,000 combat sorties in the Pacific. It destroyed an estimated 11,000 ground targets. It dropped 65,000 tons of ordnance. Each destroyed vehicle meant supplies not delivered. Each destroyed building meant resources denied. Each destroyed aircraft meant one fewer defender. The production numbers illustrated American industrial supremacy. Chance Vought and its licensees built 12,571 Corsairs between 1942 and 1953. At peak production in 1944, plants delivered over 400 aircraft monthly. This single type represented more fighters than Japan's entire production of all types during the final war years. Japanese commanders knew these numbers and understood their implications. Every Corsair destroyed was replaced within days. Every Japanese fighter destroyed represented an irreplaceable loss of aircraft and, more critically, an experienced pilot. Japanese engineer Jiro Horikoshi, designer of the Zero, examined a captured Corsair in the war's final months. His assessment, preserved in post-war documents, acknowledged American engineering achievement. "They built an aircraft we would never design," he wrote. "Too heavy, too large, too powerful for our industrial capacity to duplicate. Yet it worked magnificently in combat." They understood that absolute performance in specific regimes mattered more than balanced performance across all regimes. The Corsair's influence extended beyond its combat record into post-war aviation. The inverted gull wing design influenced subsequent aircraft. The emphasis on structural strength over lightweight became fundamental to American fighter design. The integration of fighter and bomber roles in a single airframe became standard. The Fate Crusader, developed in the 1950s, embodied Corsair philosophy in supersonic form. Even modern strike fighters like the FA-18 Super Hornet trace their doctrinal lineage to lessons learned in the Corsair. For Japanese personnel who survived, the Corsair remained a symbol of American material superiority that no amount of courage could overcome. They had fought with everything they had. They had displayed tactical skill, strategic vision, and personal bravery, but they lacked the industrial base, the engineering capability, and the resources to match American production. The Corsair represented that disparity in its most visceral form, an aircraft that could do things that should have been impossible, flown in numbers that seemed inexhaustible, by pilots trained to standards that Japanese industry couldn't match. The shock wasn't personal. Japanese personnel respected their opponents as fellow warriors. The shock was professional and existential. Facing an enemy who could build aircraft this capable, this durable, and this numerous made victory impossible, regardless of individual courage or tactical brilliance. Senior Petty Officer Takeo Yamamoto, the anti-aircraft gunner who witnessed those impossible dives in February 1944, survived the war and returned to Japan. In a 1972 interview for a Japanese television documentary, he reflected on his experience. "The Corsair taught us that the war was lost," he stated, "not through any single battle or dramatic moment, but through the daily realization that the enemy possessed capabilities we couldn't match. They could dive at speeds that should have killed them. They could pull out at altitudes that should have been impossible. They could absorb damage that would have destroyed our aircraft, and they appeared in numbers that made resistance futile. We fought bravely, we died bravely, but we were fighting against industrial and engineering superiority that made our bravery irrelevant." The final Corsair combat missions in the Pacific came in August 1945, providing close air support for occupation forces in Japan after surrender. The aircraft that had terrorized Japanese forces for 2.5 years flew over silent airfields, destroyed cities, and defeated armies. The shock they had delivered was complete. The legend they established continues, studied by aviators, historians, and engineers, seeking to understand how structural strength enabled tactical dominance. The structural engineering that enabled the Corsair's shocking dive performance represented a complete departure from conventional fighter design philosophy that had dominated aviation since World War I. Every air force in the world had operated under the same fundamental assumption. Fighters must be light to be maneuverable, and maneuverability determined victory in aerial combat. The lighter the aircraft, the tighter it could turn, the faster it could climb, the more responsive it felt to the pilot. This philosophy had governed fighter development in Britain, Germany, Japan, Italy, and the United States itself through the 1930s. The Supermarine Spitfire, arguably the most celebrated fighter of the early war years, weighed just 5,000 pounds empty. The Messerschmitt Bf 109 weighed slightly less. The Mitsubishi Zero weighed an astonishing 3,900 pounds empty. These aircraft could turn inside larger, heavier fighters consistently. They could climb rapidly from low altitude. They felt responsive and alive in the pilot's hands. Traditional fighter doctrine emphasized these qualities above all others. Getting on the enemy's tail through superior turning meant victory. Losing a turning fight meant death. Rex Beisel and his engineering team at Chance Vought rejected this entire philosophy when designing the Corsair. They started with the most powerful engine available and built the airframe around that engine's capabilities rather than compromising engine power to achieve light weight. The Pratt and Whitney R2000 800 double wasp was a massive 18-cylinder radial engine. In its initial configuration, it produced 2,000 horsepower at takeoff. With water injection systems added in later variants, it could produce 2,250 horsepower for short emergency bursts. This was 50% more power than the Zero's engine. It was comparable to engines powering twin-engine bombers. The engineering challenge was translating that raw power into combat capability. The propeller had to be large enough to absorb the power efficiently, without excessive tip speed that would cause supersonic shock waves and lost efficiency. Beisel's team calculated that a 13-foot 4-inch diameter propeller was optimal, but a propeller that large created an immediate problem. It needed substantial ground clearance to avoid striking the runway during takeoff and landing. Traditional solutions would have required extremely long landing gear struts, adding weight and complexity. Long landing gear would have been structurally weak, prone to collapse, and difficult to retract into the wing. The inverted gull wing solved multiple problems simultaneously. The wing attached to the fuselage at its highest point, then bent downward in a distinctive gull shape before extending outward horizontally. This configuration allowed relatively short landing gear struts to attach at the wing's lowest point, while still providing adequate propeller clearance. The landing gear could be strong, simple, and light, but the structural implications were profound. The wing root, where the wing joined the fuselage, had to handle enormous bending moments during high-G maneuvers. During a 9G pullout from a high-speed dive, the wing had to support 9 times the aircraft's entire weight. At 14,000 pounds gross weight, that meant 126,000 pounds of force trying to tear the wings off. Chance Vought engineers designed a wing structure that was fundamentally overbuilt by the standards of the era. The main spar was a massive aluminum I-beam running the entire wingspan. Secondary spars provided additional strength. The wing skin was thick aluminum, flush riveted for smooth airflow but also contributing structural strength. The internal ribs were closely spaced and heavily reinforced. Multiple attachment points connected the wing to the fuselage, distributing loads across the structure rather than concentrating stress at a few points. The result was a wing that weighed substantially more than wings on comparable fighters, but could handle stress loads. Those fighters could never survive. Testing at the Naval Air Test Center revealed the margin of safety built into the design. Engineers mounted a production Corsair wing in a test fixture and applied steadily increasing loads while measuring deflection and monitoring for failure indicators. At 6 G-forces, normal combat loading, the wing deflected slightly but showed no signs of stress. At 9 G-forces, the maximum load expected in violent combat maneuvers, the wing deflected noticeably but remained well within elastic limits. When the load was removed, it returned precisely to its original shape. At 12 G-forces, well beyond any loading a pilot could survive, the wing bent dramatically upward, flexing several feet at the tips. The structure showed signs of stress, but did not fail catastrophically. The wing returned to its original shape when load was removed with no permanent deformation. This testing meant that the Corsair's structural limits were far beyond the pilot's physiological limits. A pilot would lose consciousness from G-forces long before the airframe failed. This gave pilots absolute confidence to pull as hard as necessary during combat maneuvers without fear of structural failure. That confidence translated directly into tactical aggressiveness that Japanese pilots, flying aircraft with much lower structural margins, could never match. A. Zero pilot pulling hard in a turn or during a dive pullout had to remain aware of structural limits. Pull too hard and the wings would fold or the airframe would break apart. Visual indicators like wing deflection and control feel gave experienced pilots warning of approaching limits, but it required constant attention and divided focus. A Corsair pilot could pull the stick back as hard as physically possible and know with absolute certainty the aircraft would handle the stress. The only limit was whether the pilot could remain conscious under the G-forces. This fundamental difference in structural confidence shaped tactics throughout the Pacific War. Marine and Navy pilots attacking Japanese positions could enter dives from any altitude, accelerate to maximum speed, and pull out at the absolute lowest altitude they dared, knowing the airframe would survive. Japanese pilots attempting the same maneuver risked catastrophic structural failure that would kill them instantly. The psychological impact of this structural superiority extended beyond individual combat engagements into the broader strategic situation Japanese forces faced throughout 1944 and 1945. Every Japanese soldier, every gun crew, every base commander understood that American air superiority was absolute and unchallenged. The Corsair symbolized that superiority in its most visceral form. It attacked with impunity. It shrugged off damage that would have destroyed Japanese aircraft. It appeared in numbers that seemed endless. This psychological dominance eroded Japanese morale systematically across every theatre where Corsairs operated. At Peleliu in September and October 1944, Marine Corsair squadrons provided close air support for ground forces fighting through some of the most difficult terrain of the Pacific War. Japanese defenders had fortified caves and bunkers throughout the island's coral ridges. These positions were nearly immune to naval, gunfire and artillery. But Corsairs could dive nearly vertically, deliver bombs and rockets with precision, and pull out in the narrow valleys between ridges. Marine pilots made hundreds of sorties, sometimes attacking targets less than 100 yards from friendly positions. The structural strength that allowed violent pullouts in confined spaces made this precision possible. Japanese defenders reported that the constant air attacks made movement impossible, destroyed morale, and convinced many that surrender was preferable to continued resistance. At Okinawa from April through June 1945, Corsairs flew combat air patrol over the invasion fleet, intercepting kamikaze attacks before they could reach American ships. The high-speed diving attacks refined against ground targets proved equally effective against suicide aircraft. Japanese kamikaze pilots flew straight and level, often at low altitude, making no evasive maneuvers. They were easy targets for experienced Corsair pilots who could dive from altitude, fire a short burst, destroy the kamikaze, and climb away before Japanese escort fighters could respond. Marine Corsair squadrons claimed hundreds of kamikaze kills during the Okinawa campaign, significantly reducing the number that reached the fleet and potentially saving thousands of American naval personnel. The Corsairs' service extended well beyond World War II, testament to the fundamental soundness of its design. During the Korean War from 1950 to 1953, Marine and Navy Corsair squadrons flew ground attack missions supporting United Nations forces. The F4U and F4U variants featured more powerful engines producing 2,450 horsepower, increased ordnance capacity, and improved systems. These aircraft performed the same mission profile refined in the Pacific: high-speed diving attacks delivering bombs, rockets, and gunfire with precision. The structural strength that had shocked Japanese forces in 1944 proved equally valuable against North Korean and Chinese forces in the 1950s. The final combat missions flown by Corsairs occurred in 1969 during the football war between Honduras and El Salvador. Honduran Air Force F4U Corsairs, purchased as surplus from the United States, flew ground attack missions. These aircraft, built in the mid-1940s, were still capable of the same high-speed diving attacks that had terrorized Japanese forces 25 years earlier. The fundamental design remained sound despite technological advances in jet aircraft. The Corsairs' influence on naval aviation doctrine persists in modern carrier operations. The emphasis on structural strength over lightweight, the integration of air superiority and ground attack roles in a single airframe, the requirement for aircraft to survive damage and continue fighting. These principles trace directly to lessons learned, operating Corsairs in combat against Japanese forces. Modern strike fighters like the F-18 Super Hornet embody these same priorities adapted for supersonic flight and modern warfare. For aviation historians and engineers studying the Pacific War, the Corsair represents a pivotal moment when American industrial capability and engineering philosophy combined to create decisive tactical advantage. The Japanese had built excellent aircraft optimized for specific performance characteristics. The Zero's maneuverability and range were genuine achievements, but those achievements came through compromises that created fatal vulnerabilities. The Corsair represented a different philosophy entirely. Build an aircraft around overwhelming power, make it strong enough to handle that power, accept the weight penalty and compensate through engineering. The result dominated the sky not through elegance or refinement, but through sheer capability that couldn't be matched. Thank you for watching this deep dive into how the Corsair's structural strength shocked Japanese forces and changed the Pacific Air War. The aircraft's ability to dive at 450 miles per hour and pull out unharmed wasn't just impressive engineering. It was a tactical revolution that Japanese forces had no effective answer for. If you enjoyed this detailed historical analysis, please check out our other videos exploring the technical and human stories of World War II aviation. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.